Welcome everyone to the Leapfrog and Reflex ioGAS presentation on the ioGAS live link. This presentation is designed for an audience that's both new to the live link as well as an audience that's already familiar with it. If you fall into the latter group, definitely stay on the line. There are quite a few new features you might not have been aware of for the new ioGAS live link that has been improved with the onset of Geo 3.1 as well as ioGAS 6.2. Just to show you who your hosts are today, it's myself for Iran's Geo, Janina Nico, and then have here my colleague from Reflex.
Hello, Britt Blumel here.
All right, and the two of us will take you through today's presentation. In regards to what we are going to show you, our demonstration will go into detail when it comes to transferring interval data from Leapfrog to ioGAS. We will also do the reverse. We're going to introduce information from ioGAS back into Leapfrog. We are going to generate geochemical classifications in ioGAS, and we'll showcase just exactly what a powerful tool ioGAS is and all of the different functionalities that are available there on your at your fingertips. We will also then introduce new data back into Leapfrog and actively model from it and spatially evaluate the data sets that we have derived first in Leapfrog and in ioGAS. We're going to go through 3 different exercises regarding an exercise on lithological classification, then alteration modeling, and finally grade integration and interpolation. And because a picture is worth 1,000 words, we're going to now jump into our active demonstration of the 2 programs. And here we have both of our programs right side by side, and this is how we're going to remain in our view for the next little while. On the left side here, we're going to get started with our project in Leapfrog, and what we see here is the YAM project, which represents a banded iron formation. And what we see here are drill holes in combination with interpreted lithologies. Now, what we're going to do for this exercise is we are going to have a closer look at the assay information that came specifically with this data set, and we're going to run a couple of geochemical calculations on it and then use this data and actively compare it with our interpreted lithologies here. One of the great things about this interactivity between both programs is that you can spatially evaluate lithological data from logs and chemistry at the same time, and thus have a look whether you've actually made the right decision for your interpretation based on chemical response. So that's what we're going to look at today, but let me give you a little bit more advice on how to first prep your data set. So what we see here is the aerial photograph for the YAM deposit, and we see all the different colors here associated with it, so all the different drill holes. Sometimes we do only want to spend time on a specific subset of information and not necessarily calculate assay information, for example, from absolutely everywhere. So we want to focus in a specific area. If you'd like to do that, you can go ahead and you can create query filters within Leapfrog. So you can do that on point information, but also anywhere within your drill hole database. So for example, here, for demonstration purposes, I am going to filter out or create a filter that will take out a couple of my drill holes. So I've already prepared this filter here for me, so it's a spatial filter. And if I now click here down in my shapes list on color, I can then actively in my properties panel apply the filter. And you see that at the bottom of my map here, a row of drill holes disappears. So it's just a little example on how you can create a subset of information. Now, this information at the moment is all saved as interval data. And now in order to introduce specifically our assay data here into ioGAS, we need to turn our interval information into point data that ioGAS can read. Now, this functionality happens within the actual geochemistry folder. Here, I just need to right-click onto my ioGAS icon and create a new little Beaker file or new ioGAS data file. Now within here, I can choose from any interval base table that I have at hand, in this case, my Kalkmin table. And now I have the option here to also create a subset of data to be brought into ioGAS based on the query I built earlier on. So I can choose the query here, and then I can go ahead and I can bring in any of the columns here that I have located in my interval table. I'm going to choose to select all of them today, which includes also this top column here, and that's our from to data. Now, this is quite important. The from to information, if it is carried over at ioGAS or to ioGAS at this stage, ioGAS will always remember the from to data and will allow the ioGAS point information at any time to be reconverted in Leapfrog into interval data. So that's quite powerful. And now I'm going to click OK here, and this will create for us a little Beaker file. Now I can grab my little Beaker file and drop it into my scene window. And let me show you what has happened here. So all of these individual points are representative of the midpoints of the previous intervals. And currently they're shown here in gray as they're awaiting data from ioGAS, which will then give them color specific to chemical analysis. And at this point, I'm going to hand over to my colleague Britt. But before I do that, I'm going to actively connect now to ioGAS by clicking this button here. And once it says connected, we can go ahead and then tell ioGAS to talk to Leapfrog.
Wonderful. Thank you very much, Janina, for building this lovely project for me to work with. So right now, because ioGAS is connected to Leapfrog, Leapfrog is actually broadcasting information towards ioGAS. And when we say file, open link data, ioGAS will start listening to what Leapfrog is saying. So what's happening now is the link is being established and data is flowing from Leapfrog into ioGAS. There we are. And you'll notice here on the left-hand side that the drill holes actually used to be colored gray, which was the default Leapfrog color scheme, but now they're colored black, which is the default ioGAS color scheme, which tells us that all of the coloring that's happening at this moment is actually being controlled by ioGAS and the link is active. So we'll start by making an attribute map so we can see that everything is plotting where we expect it to. And then we're going to open our column properties window. So the column properties window is the one that opens by default when you open a new ioGAS project from an Excel file or a CSV file. And what we're going to do in here is use this guess aliases button. Now, aliasing is important in ioGAS because it tells ioGAS what you're actually giving it. So instead of a number that represents your chemistry, you're giving ioGAS actually 3 pieces of information when you alias your variable. You're telling it the elemental form, the unit, and the oxide. So we see here in this data file that we have manganese actually represented twice, manganese as percent and manganese as an oxide. So since we're looking at whole rock chemistry, we'll just reset this alias so we only have one manganese column. And we'll just scroll through and make sure everything else looks okay. And then we'll say okay. So we'll go into now our select variables dialog. You'll notice along the top of our ioGAS window that most of our icons to make graphs are grayed out because we have yet to select any variables that we want ioGAS to look at or deal with for us. So we'll just grab everything up to LOI in our select variables dialog and say okay. And then we notice that all of these graphing icons are now available for us. So we'll start just by making quick probability plots to make sure that our data looks okay. Everything is distributed normally because we're looking at whole rock chemistry. We have some negatives down here in our LOI data, which is normal. So now what we'd like to do, because we're looking at a relatively large data file, we're going to use a new tool in ioGAS, and we're going to randomly subsample the data. So what we're going to do is just choose 20% of the data, say apply, and now what's happened here, you'll notice that the Leapfrog page as well is flickering, as well as the ioGAS page. Now only 20% of the data is available to us because 80% of it has been hidden in the filter tab. For those of you that haven't used the filter tab before, it's the 4th tab in your attribute manager, and this little red icon will appear when your filter tab is activated. And the filter tab is actually the strongest, you could call it the super filter, of all of these 4 attribute tabs. So if you hide something or make something invisible in the filter tab, it will actually be hidden from all of the other tabs, which is why we call it super filter. So this random subset of data automatically super filters your data. And from here, we're going to make a self-organizing map on this subset of our data. So a self-organizing map, for those of you that aren't familiar, is an artificial neural network that reduces the dimensions of multivariate data by producing a 2-dimensional map that groups similar data items together. And within the self-organizing map technique, we're going to use an unsupervised clustering method. So first, we're going to transform our data, and we're going to use this scale from 0.001 to 1. In this case, we wouldn't be appropriate to use log, normal, or power transform, because we're looking at whole rock chemistry. So we're going to scale from 0.001 to 1. Also, we would rather not introduce zeros into our data set, which is why we're choosing this one. And we're going to make our SOM just a little bit smaller. So you'll notice as I change this size of my self-organizing map, my initial neighborhood radius will also change automatically to reflect. I'm going to make the number of iterations a little bit smaller so it runs faster. And then I'm just going to ask ioGAS to learn. So what's happening now is each sample that I have is being assigned to a node. Each square of my self-organized map, it's a 10 by 10 map. Each square contains a node, and that node has a particular chemistry. So now my samples are being applied or matched to the node that best represents them chemically. Here's my SOM output. And this classify neurons button here is actually just a shortcut to our original k-means clustering algorithm here. It's a hard partitioning that lives right there. But we can shortcut using this classify neurons button. We'll say OK. And here we can choose the number of clusters that best represents the changing chemistry within our lithologies. So in this case, maybe we'll choose 6. We'll apply to color. And now we see our self-organizing map has colored up there. So we're going to apply the SOM. We're going to say to visible rows, because remember we've hidden a bunch of our data in the super filter tab. And as we apply the SOM, all of the probability plots and then our Leapfrog data points will recolor themselves based on these new clusters that we have chosen based on the differences in chemistry that we have. So you'll see that this red group here has high aluminum, high silica, low iron, high titanium. And we can start to make sort of interpretations and inferences about what's happening with our data geologically based on these different groupings. So there is our self-organizing map color scheme painted onto our Leapfrog scene. And if we just zoom in, we see, yeah, that looks pretty reasonable, pretty representative. So I'll go back to my self-organizing map, and I'll go back to my attribute manager, and I'll just make everything visible. And then I'll apply my SOM again. And I'll apply it to visible rows, or all rows, because all rows happen to be visible at this moment. So now we see that our SOM has been applied to all of our rows. And if we hop back into Leapfrog, we can see that there's actually a few different groups that look like they could be merged together. So for example, the top of this drill hole has this olive group and this light blue group that look like they could all belong to, for example, a weathering profile. So we can use, in this instance, a new merge tool in ioGAS. In this case, we're going to merge cluster 5, the olive group, into cluster 6, the blue group. And then that's going to, oh, there we go, automatically put those groups together. And then we can rename that group from cluster 5 plus cluster 6 into something more significant like weathering. We could also do that for the rest of these 4 clusters. We could name them appropriate to what their lithology may be, but for the purpose of speed, we'll just leave them cluster 1 through 4. And here, we can just go to our data menu and, as we would normally do, make a variable from color. And this will make a new column for us, and this new column we'll call ioGAS lith, and ioGAS lith, we'll just overwrite yes, is our lithology that we have determined based on our self-organizing map from these 12 input variables. And this new column has actually written itself into our data file. over here. So if we scroll to the right, we'll see that we have this ioGAS lith column, and it has not only our weathering groups, but also our clustering groups. So from here, if we save our ioGAS file, then all of this information that we've written into the file will be available for us to make a model in Leapfrog. So I'll do that here. I'll say File, Save As. We'll save it as Webinar on the desktop. And then we'll see over here in the Geochemistry folder in Leapfrog space, we'll have our little beaker as well as our new webinar icon. And this save feature is really important, and Janine will elaborate upon that.
Thank you very much, Britt. So that has provided us with quite a bit of extra data here that we can then model up in Leapfrog. But yes, let's talk just quickly about the last couple of steps taken here. So the initial step here of making a variable from color, because we started our project in Leapfrog and it came with interval data automatically, what this affected was that the ioGAS lith information was automatically transferred in interval space. And what that means is that this function led to a new column being created in the original table, our original assay table, where the data originally derived from. So here we have a new little Beaker file, which we can throw in here instead of our Beaker file specific to our ioGAS folder here at the bottom. Now, in addition, Britt mentioned this very important little file here, which pops up as soon as you create a saved gas project. Now, this will allow us later on to go full circle. So this little gas file here will remember just exactly its origin as a gas project, and it will allow us to always connect back to Leapfrog. And this allows us to later on turn both of the projects off, turn both of the programs off, revisit the project individually in either program, work on them, and then reconnect them again. We'll come back to this little file at a later stage and talk about it a little bit more. At this stage now, I'm going to go ahead and I'm going to close my project in ioGAS, and I'm going to disconnect the link between my Leapfrog project and ioGAS. And now I'm going to go ahead and start modeling up my geochemistry. So I'm going to focus more specifically now on our intervals for weathering. We see that right here. There we go. And what I'm going to do now is to actively compare this information with some of the lithologies I have already modeled from logging data. So let's have a look here at my log lithology model, and more specifically my weather contacts, how it is defined so far by our lithologies in our logged core. And that actually looks already pretty good here, but we see that locally ioGAS has pulled out a couple of other areas that might be of interest to us here at a lower area, and we need to identify just exactly why these were pulled out and what that means to us. So I'm going to go ahead and I'm going to model up this information to see where is the spatial overlap here between a surface resulting from the chemistry and the surface I've already built. So I'm going to build a new geological model, or also called an alteration model. So it's going to be the ioGAS alt model. There we go. And I'm going to choose, of course, appropriate data, and that's here our ioGAS lith data that we created. I'm going to set down the surface resolution a little and choose an appropriate boundary and click OK. And now I'm going to go ahead and I'm going to build the surface again as a new erosion from base lithology. I'm going to choose our weathering code, and we are also going to filter a little bit. So we're going to composite a little bit of those tiny little intervals out here. What we're looking for are chemically coherent areas here that might be representative of a continuous lithological feature, such as the weathering horizon. So we're just going to filter a bit and click OK. And now we can have a look at the result relative to that original surface here. And while on the east side here, we have a fairly strong overlap. So there seems to be quite an agreement here between the log lithology and the chemically evaluated top zone. When we look at the west side, it's a bit different. So we do have a couple of areas in here, for example, where chemically we see a deeper weathering profile as what we've originally logged. And that would give me hold, and it would make me think, okay, well, let's have a closer look here at the these drill holes in the periphery of my established data set, and let's double check what's exactly going on here. This could be related to a logging mistake, for example, but it could also identify a structural feature in here that may not have been logged in the same fashion, and where the weathering profile is actually being drawn to greater depth. So it can really point out where there are areas where we have lesser drilling, lesser interpretation information, and where we need to focus in on. So that's where chemistry can become very handy. But of course, this is just one example out of many, many, many. And sadly, we don't have the time for it today to take you through another 150 examples where chemistry becomes extremely handy. Okay, so at this stage here now, I'm going to give my project back over to Britt, and we're going to come to the point where our users usually ask us, so what happens if I already have an established ioGAS project? Can I bring that into Leapfrog?
Well, yes, Nina, you absolutely can in version 6.2. So that new version is actually not available for download quite yet. It's very close. We're very soon we'll be ready for that. So there's a new feature in ioGAS version 6.2, which allows you to drag and drop projects from anywhere on your computer or your desktop into ioGAS to make it available rather than going through the file menu. So here I've just grabbed our webinar full file from the desktop, dragged it into the ioGAS window, and it's restoring my original workspace. So I don't need any of these things at the moment, so I can just close these windows here, and I'll open my attribute manager and remove this color scheme because we're going to work on something different. In this file, as well as chemistry, we also have calculated mineralogy, so we're going to use a little bit of that and try and make some interpretations about the alteration. So I'm going to choose hematite, goethite, and quartz and make myself a ternary plot. And I'll just turn on this point density here to show where in the ternary plot I have higher concentrations of samples that are more hematitic and more goethitic. I'll also make myself a couple of new colors in my attribute manager, and I'll paint my hematitic group with this red color, and I can paint my goethitic group with this green color. Then I'll go back into my attribute manager and I'll rename those two appropriately. So the red group is now hematitic or hematite. Great, and my green group is now goethite. And that information I can just leave here because it exists in my attribute manager. The other thing I'd like to do at this moment is use a calculation from my provided calculation menu. So in the provided calculation menu, I'll go to the regolith area, and I'd like to make a plagioclase index of alteration. What you may or may not know about ioGAS, and this is a standard feature, is if you get to any calculation or diagram, if you hover your mouse for a few seconds over top of the title of the diagram or calculation, the whole calculation will actually appear for you in this handy drop-down yellow box, as well as the entire reference. So we're going to create this plagioclase index of alteration column, and then that is going to be available for us in our data file. You can see that right here. So what we'll do now is we would like to bring this information back into Leapfrog. So we'll just make sure that ioGAS is connected, and we'll clear the scene, and we'll drag in webinar, and sure enough, there is our hematite and goethite groups, colored in red and in green, and we'll just explore a different way of bringing that information back into ioGAS, or back into Leapfrog, excuse me. So I'll right-click on this webinar, and I would like to say import as points, and I'm going to import two different points files. The first is this new PIA column that we've created for the plagioclase index of alteration. I'm going to import that as a number, and I'm going to call it PIA. Wonderful. And then the second will be in our hematite and goethite groups, and we'll bring them in as a category. And this category will be the color from our attribute manager. And we'll see we have these three different items in this color field of our attribute manager, hematite, goethite, and default color. And we're going to call this hematite and goethite for our import name instead of color. or instead of webinar, excuse me. And we'll say finish. So now we have these two different points files available for work in Leapfrog.
So thank you very much, Britt, for all this wonderful information we can now model up in Leapfrog. Just one more thing about this little gas file here. We right-clicked before, and Britt was so kind to import the information as points. And that would usually happen when you start an old ioGAS project in gas and then bring it over into Leapfrog. If you, at any given time, started your project in Leapfrog beforehand and you had the luxury of introducing the from to information, then you can also directly import all of your data points as intervals. That's also possibly done right here. Now at this stage we can disconnect our we can disconnect to ioGAS. There we go. And we can also close our project in gas. Here we are. And now we can focus in the points that we just introduced. So for example, here we've got hematite versus goethite, and we've got our peer points. And in the past versions of this live link, you were only really able to work with this data in the interpolant space. So you can only create soft shells from this level of information. However, in the latest version of Leapfrog Geo, you're also able to transform your information into what we call guide points and build hard shells from it, such as geological model units or hard shell meshes. So let me just quickly show you how that's done. So this is your point information here that has been introduced from gas, and of course the colors are slightly different, but effectively the data is exactly the same. And now you can use this information to create guide points. First of all, you would have to create a new category selection. And what that means is that you have to go ahead and you have to define different category areas that are representative of a specific environment, such as a lithological unit, for example, an alteration zone, in this case, goethite, hematite, etc. So I'm just going to quickly create a new selection file. There we go. It's slightly different than the original. And basically what has happened here is we opened up a new dialog here, and that looks extremely similar to our interval selection tool. Now within here, you could pick any form of environment by hand that you can then code as a different feature. So you can go ahead here, for example, we can highlight all of our default color here and assign it to a new category, which I can call other, for example. Give this a color, click OK, and here we are. Now we have a new category selection. And usually, of course, you would create a subset selection here. Basically, when this is saved, we can then use this category information to create a new point file called new guide points. And now this probably looks very familiar to a lot of people. This is basically what we have to fill in order to create a hard-shelled mesh of some form. So we have to define interior points, positive points for our meshes, exterior points, and then also ignored points. Now, in this particular case here, I've already prepared some guide points for us, and I have created a mesh for us based on these points. So you see that right here under my general section, I have here selected guide point, and the result is a hard-shelled mesh that is guided by the interior, exterior, and ignored selection on my categories, and which then can be representative of a hard-shelled environment. So you can also use this, of course, in the geological modeling environment, not just the meshes folder. So this is a very powerful tool. Of course, we also can apply our interpolant function still on our points, and that's particularly handy when it comes to numeric environments, such as our plateauclase alteration index here. And that index is specific for weathering profiles, alteration profiles. And in this particular case here, it's very handy identifying not only specifically our weathering top layer, so that would be very good, but also to define a least altered core within in our environment here. And this particular information is what I'm interested in. So I'm going to go ahead and I'm going to apply a value filter onto my points to focus in onto those blue and green points that are representative up to a value of 30. So these are my freshest pieces in here, and I'd like to know just exactly how they correlate with each other, and also how this chemical information here correlates directly to already built lithological units, such as my banded iron information, for example. So what I'm going to do here is to build a quick interpolant of this information. So I'm just going to go down to my interpolants folder, right click, new interpolant, and now I can choose from my point information, in this case here Pia, enclose object, and then I'm going to go ahead and build a nice fine interpolant, low surface resolution, and I'm going to choose lower intervals. So click OK. And while this is running, I'm also going to make some localized changes here. I am only going to build one isosurface, and that represents sort of a binary isosurface that separates out roughly everything that would fall into the 30 value, and then everything on the outside. I'm going to make this one yellow. Click OK. Then I'm going to adjust my interpolant to a spheroidal model. Also going to decrease my base range here. And I'm also going to apply a small trend to my interpolant. There we go. Is it functioning? All right. So while we're waiting for the other interpolant to run, I'm just going to quickly show you one I've already earlier prepared. And here we go. So now this is representative of our less than 30 sort of environment here. And this information now I can introduce into two different features. First of all, I can apply this or evaluate this information onto a geological model, and more specifically a lithological output, such as my banded iron formation. So I'm just going to right click here on my output volume for banded iron formation, click evaluations, and choose my output volume from the interpolant. So while this is running, I'm also going to show you another visualization option. How can I evaluate this information, for example, onto a cross section? So I'm just going to drop in my cross section here, and this has already been prepared for us. Basically what I've done is I evaluated this interpolant directly onto my section here, and it automatically shows where it lies in 2D relative to the remainder of the lithological units, my draw holes, etc. So this is quite powerful indeed. So now I'm going to turn my cross section off again, and we're just going to wait for my banded iron formation to have the interpolant information evaluated onto it. So I'm just going to make it a little bit more opaque here. This is my large lithological environment, and what I really want to see here is just exactly where in this environment here do I have the least alteration? Where are my freshest part? Where is the core to this environment? And now I can go ahead and I can click onto my coloring option here in the shapes list and choose my Pia and actively apply my interpolant onto this lithological unit. So quite powerful that I can spatially overlap and apply a combined visual interrogation for my lithological unit. Okay, so this is it at the moment for our Yam project, and now I'd like to introduce you to our last exercise here, and that refers to our Hakera project. So at this point, I'd like to thank First Quantum Minerals for providing this particular project.
And we'd also like to give a huge shout out to Federico Canucci, who did his PhD project on this deposit, and who also was trained by both of us in our respective softwares. So, hey Fede, what's up?
Yep, we're extremely proud. So let's go and have a closer look at this particular project here. So as the name already mentioned, so we have here a large porphyry project, and this is a copper gold molybdenum porphyry. And I'm just going to zoom into a slightly different view here. In red, we see our Hakera porphyry, which is sort of the core of this deposit, and then we have a whole number of different draw holes here that came with a bunch of different interval information that can be extremely useful for further chemical interrogation. So one of the things you may have noticed here is that my assay table and my lithology table are separated from each other. So the information is not correlated with each other at this stage. However, frequently we would like to have both levels of information being introduced into ioGAS for an active comparison. So how do we bring those particular tables and this information together? Well, there's actually quite a neat way of doing that within Leapfrog. Bringing both of these data together can be done in the composites folder, and right here I can right click and choose new majority composite. At this stage, some of you might already think, so why didn't you just build straight up a merge table? That would bring both of the tables together too. That is true, absolutely. That merging function, which lives here under drawbles, is also an option. However, the merge table automatically chooses always the smallest common denominator to create new from two intervals. And in some cases, that can lead to the duplication of assay points. That's something we definitely want to avoid because that can give bias to our data set. So what we want to do is we want to first make sure that our assay intervals are fixed and that these fixed lengths are then applied in turn to our lithology information. So our lithology information, it's okay if there are potentially duplicated points. That's fine. Within the same relative space, they can be. But assay information, numerical data really should not be duplicated. So in this case here, I'm going to now superimpose my assay from twos directly onto a lithology column from my list table. I'm going to click OK. And this is going to run for a moment and now split up locally the lithology intervals that I had, creating a majority compositing table. And this is the result here. So we have intervals for our assays that run from 0 to 2, for example, and then our intervals for our lithologies have been adjusted to that. We do get another column here in this majority composite that will allow us to see just exactly how much of this lithology data actually falls into the new interval. And in this case here, for the most part, it's 100%. And usually that should really be the case because you tend to stop an assay interval at specifically the contact with the lithological unit. However, if this is not the case, as an area such as this, you might want to have a look into your data tables and assess what exactly has happened there. I'm going to leave this to First Quantum Mineral here to figure out. We'll move on because the next step is now to actually bring this data here together with our assay information. And this is now the stage where we are going to build a new merge table. And we're going to build this merge table from all of our assay information in combination with our majority composite for strat group, which are now exactly the same length intervals as what we had before. So I can now create a new merge table as the ioGAS, litho, and assay table. Click OK. Fix it for me. We don't like spaces. They are replaced with underscores. And now a new merge table is being built, which is going to be the foundation for the gas file I'm going to create in just 1 second. So once it's run, I can right click here on ioGAS and create a new ioGAS dataset. And then I can choose here my ioGAS litho assay merge table, which has all of my assay and lithological data at the same from two intervals. So no duplicates. This is ideal. This is what we want. So we'll bring all of this information over, click OK, and then we're going to actively connect to ioGAS and bring the data over. And this is where I'm going to ask Britt to take over.
Thank you very much, Janina. So this next step is something that you guys have seen before in this webinar. So we're going to, again, open the link data from Leapfrog into ioGAS. So first what we're going to do is look at our aliased columns, and we're going to use the data doctor. So we're going to go to the validate menu and say data doctor. And here, ioGAS will go through and will scan our columns, and it will look for problems in the data. So when I say problems, I mean nulls, negatives, zeros, text values, less than signs, anything like that. And ioGAS will flag that sample and suggest a replacement value for us. So in this sample, in this data file, we have a few zeros. And we just want to replace those with nulls because we don't really want zeros in our data set, of course. So we'll say apply, and then we can just say close, and we'll start with box and whisker plots. So box and whisker plots are excellent if you have a few different elements to look at and you have several different attributes that you want to color them by. So you could use lithology or alteration or even project or property or analytical method. Box and whisker plots, for those of you that aren't familiar, are from the 25th to 75th percentile of your data falls within the box, and then everything on the outer edge of the box is above your 75th percentile or below your 25th percentile. Another way you can think of for looking at a box and whisker plot is you can sort of imagine a histogram next to it. So it kind of looks like a histogram that's been laid on its side, and if you have a long positive tail of outliers, then this data would be positively skewed, whereas this data over here might be more negatively skewed, more outliers in the lower end. So the whisker here, that's 1.5 times your box length or interquartile range, and everything outside the whisker counts as an outlier. Everything greater than 3 box lengths away from the 75th or 25th percentile, you'll notice is a triangle shape, and that means that it's a far outlier. So all of this information about box and whisker plots is available for you with this Show Copyable Report button. It's this orange notebook on the side. And everything we just talked about, the far outliers, the mean and the median are here represented as the black circle and black line. All of that information here is represented for you and copyable into a report, so you can grab that and drop it into an appendix. So what we're going to do is just look at copper, and what we'd like to do is identify the outliers in our copper data, and we would like to visualize those automatically in Leapfrog. So first, we're actually going to save this file, and we're going to call it Akira. So that we can see this happen on the fly. And then we're going to drag Akira into the scene. We'll notice the little ioGAS icon over here in our Geochemistry folder. There we are. And there is our strat grouped color scheme. And what we'd like to do is apply this shape, this outlier shape in copper to that scene. So what we're going to do is go to the analysis menu, and we're going to auto attribute our 2 key outliers. 2 key is another way of saying box and whisker plot. So now we see, if we scroll around here, we'll see that these outlier samples here, these circles, have been identified for us in Leapfrog space as well as in Geochemistry space. So this outlier anomaly assessment tool here has been in ioGAS for quite a while. There's also in the anomaly assessment tool a new tool here, which we won't go into any detail about today, but you can go ahead and explore at a later date.